welcome back. And switching over to the screen, we're going to predict products of this type of reaction, and these are all chapter 22 electrophilic, aromatic, substitution reactions. So the reactant here, phenyl carbonyl chlorine, is benzoyl chloride. We learned that on our previous test. And it's going to react by creating an electrophile, and we have to look at the benzene. And this is a benzene. If you want to look at it, it has 3 groups on it. It has an amino group with a lone pair. I want to remind you that's very strongly activating. It's the most strongly activating group we know. So you can pretty much stop looking at the other groups right now. The other groups, though, are alkyl and alkyl. All 3 groups are ortho-para-directing. This is the most powerful. So your original choice for where to put the next group would be para to this. And you say, okay, there's already a group para. I'm not going to put a second group para. I'm not going to do octet violations. Those days are over in my career. So the next best thing is ortho. Well, that position's taken here. I'm going to go ortho here for major. So I'm going to predict this product right over here. And our new group in green, ortho to the amino group. And if you had to predict a second product, you go here or here. In terms of steric hindrance, I would say here's a less hindered group. Here you got a position that's hindered by both, but I really don't want you to put another one there because this is the dominant directing group. It's going to put a group there. So that's all I wanted to see for that one. And in the next one, sadly, my green circle choice might be misleading with the green writing here. Let's change the color of that. Doing I. And our electrophile here. What is our electrophile here? The phenyl bromide is going to become a phenyl cation. You don't see that every day. But aluminum chloride will take that bromine off and generate a phenyl cation. Now, this is one of my favorite questions. We got 2 different rings, one with a very activating group here. So my guess would be para for this group first, ortho second. I think the ortho that's away from the other ring would be better. The ortho here is taken. That would be minor there. If you had to go minor, you're not going to get a high yield, but I'd go para to this methyl group as a third product, and then ortho to that group over here as a fourth. But I'm only going to stick with those first 2, major being para here. So, okay, we got stuff going on. So we got a biphenyl. Biphenyl. Ortho OCH3. Para to that is where I want my new group. My new group's another phenyl from that cation. And that would be major. And minor would be ortho to the OCH3. Let's see what I can get away with here. So So far, so good. And we got a phenyl ortho to the OCH3. And that'd be minor. Okay. Now we have biphenyl. We're nitrating first. The question is, what kind of a group is a phenyl group on a benzene? Phenyl on phenyl. Well, you got some good issues going on here. It is an ortho para director because it's a carbon group. That's not a carbonyl. It's going to be somewhat deactivating towards cations, although you can resonate with this benzylic position. So I'm just going to say ortho para director. It's a carbon group. Your major being right here and your minor being ortho right here. Similarly, you could have gone major here or minor here due to symmetry. So nitration, let's just stick with major here, else we'll have like a myriad of products. So step 1, major. Switched over to green again. And we're going to put a nitro on there. NO2. And what happens next? Well, the big question now is which ring is going to react first? One with a deactivating nitro or one with no deactivation at all? Well, I think that answers the question. The one with no deactivation at all. This double bond here is bothering me. It doesn't go all the way. There. This ring will react next. We're going to put a methyl group on para to this group here. Right there. Still a carbon group attached. And you don't want to go on this ring because this ring's slowed down by the nitro. So I'm going to go methyl here next in step 2. Double, 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 double. Got NO2 over here. And we have a methyl over here. And for the third group, the methyl is an activator and nitro is a deactivator. So for our final result, step 3, you can't go para to the methyl. It's already taken. Next best is ortho for bromination. So we're going to copy. Should have done this before, huh? I don't think a nitro is going to show up. It's fine. We got the nitro. And we have a methyl. And ortho to that, a bromo. So I want to see that as the major product. I wouldn't want minor products here. Okay. So that was a good start for our review. Moving on to mechanisms, unless you have a question or two here.
Yes, I do have a question, Professor.
Yes.
Can we just get the para and ortho and meta positions for the naphthalene?
I'm sorry,
So
say it again.
if we have a naphthalene.
A naphthalene?
Yeah, and
You
then we
want to
want
put
to
a
do
group on naphthalene?
Mm-hmm.
Okay, here's naphthalene. And we double, double, double. And you wanted to put your first group on? Is that what you're saying?
Yeah.
Say one we haven't done. That's H2SO4 in heat. And you're asking which position. Well, these are both ortho para directors. So if we go para to this one, it's also meta to this. I would think further away is better for steric reasons than closer. So I prefer at least para to one of the groups here. in the beta position. Remember, naphthalene has only alpha and beta positions all the way around. So we're going to put groups beta before we go alpha for steric reasons. And that's where we'd put our first group. And if we had to put a second group on in this example, we don't want to put it on the ring where we already have the SO3H, because that is a deactivating group. So I would think that's your major. That's your major. And your minor would have it over ortho here. And then if we add another electrophile, did a second reaction with a different electrophile, where would it go here and where would it go here? This ring has been deactivated. You could argue it also deactivates the other ring because they're all attached in one big ring. But the deactivation diminishes over distance. I would think here next, far away from this, para to the other rings, bond right here. So that's what I would do there. I would go SO3H here. Okay. And the next group over here. And on this one, also para. Oh, sorry. It's playing with me now. All right, we have the SO3H on the top. And I want to see it over here, either here or here. And you're not going to get a huge difference. You could argue this one's a little too close to the SO3H. Maybe you don't want to go there so much. You go down here. But the important thing is to put it in the other ring. Right there. I hope that helped. And then we'll move on to some mechanisms. Let's see, what's the best way to tackle this? Let's do them. You can copy, paste the whole thing on the next page too. We'll do C on this page and maybe D on the next page. There we go. C. What's the first thing that happens in this? This is called Friedel-Crafts Acelation. We've added an acyl group right here. Acyl. It's called propanoyl. And the mechanism starts with chlorines lone pair. Now I know you can't do this on the test and draw on the original question, so let's not do it here either. So we're going to do C down here, freehand, like you have to. And we got the aluminum chloride. And the first part is it's kind of like activating the chlorine. I know we haven't heard of that before, but it makes a bond, generates a cationic chlorine. This chlorine here will have two bonds and a cationic charge. It's activated towards leaving. Yeah, we can use Lewis acids to activate things or Bronsted acids, apparently. And what happens after that is, in the second step with a different color, it leaves. So remember, if you're going to do combined steps like that, you have to be very clear. Some of you learned the hard way last test. You got to tell me what's going on first and second. If you just say which one's first, I'm happy too, because it's implied the other one's second. And we have a triple bond to O with a plus charge. 2, 3. And that is a super electrophile for EAS. So we're going to take our trifluorobenzene. And it looks like we're going meta, which is appropriate since CF3, not a normal carbon group. It's got 3 electronegative fluorines on it. So I need to pick one of the pi bonds that's attached to the meta position. So I can use this pi bond or this pi bond because that's meta as well. And I'll pick the one that's closer to my electrophile. And that's what happens here. And we generate what? We generate an aromatic species that's not aromatic anymore, a ring species that's not aromatic anymore. We've lost our aromaticity. Very slow doing that. Gonna have an H on the meta position. H on the meta position and a carbonyl. It's our acyl group. And there's a cation, isn't there? We used to have 4 bonds to this carbon, and the same carbon here has only 3. Remember, the cation's always on a position adjacent to where you put that group. And how do you get that to be the product indicated at the top of the screen right here? And it's now that I realize I should have shown the side product over here. Because that will tell us how to regenerate our aluminum chloride catalyst and provide us with a base. Cl- is a base that doesn't have to even be strong to do this fast re-aromatization step. And just to save a second of space, oh, since we're doing another mechanism right after, why don't we just draw it down here? We're going to draw this product, and remember, we're going to treat it with lithium aluminum hydride followed by HCl. Just remember that. Back to aromatic. It's not much of a short form, but every bit helps. Mechanisms, you can always do short forms. Lithium aluminum hydride, HCl. So we got H bonded to aluminum with 3 more H's. This mechanism never goes away, so it's good to learn it like you're learning it forever. Most of you have mastered it, I'm happy to say. Generate your hydride ion. Attack something positive with it. And you can't combine this with the next step, which is reacting the product with HCl. You can't, because it is a second step. This reaction has to be finished with, purified. Stuff has to be done to it before you do the HCl step. And then our R group is here. And that needs to become an alcohol as we depict it up here. Oh, we didn't depict it, did we? Yes, we did. There it is. OH. And we're going to hit that with KH, 2,2-diethyloxyrane, and HCl after that. Remember that. I will. Maybe. And HCl is next. And we got our aromatic ring. We got our R group here. We got our alcohol here. And we're going to hit that with KH. And then diethyloxyrane. Was that good? Is my memory still working a little bit? Yeah, KH, diethyloxyrane, HCl. So keeping in mind KH is going to be a base to grab the H. I'm redrawing it with the H showing its bond. And we're going to hit it with H negative. You could just write H negative on the test. Ooh. Did it again. I think my starboard is haunted today. Okay. So what do we have here? We got an O minus. I suspect we're going to use that as a nucleophile. And I think the rest of the steps for a little while don't involve the benzene. I got an R within an R. I got to be careful here. R prime. We're going to react that with diethyloxyrene. Yep, review reactions show up a lot. 2,2-diethyloxyrene. And you're stuck, so you don't know what to do. Well, apparently the O minus is going to attack one of these two carbons. I think the CH2, see, CH2. Yep, the less hindered carbon with a strong nucleophile. I hope this is just bringing back some good fond memories for everybody. And we're going to get the O minus species. Oh, went monochromatic on you there. CH2C with an O minus on the bottom. Diethyl. And then we hit it with HCl. And we generate this. It's going to be one long skinny page. Okay, got a new bond here. Now we're bond here. What are we going to do with that? I have to do some thinking up here. How are we doing? 3 o'clock. Might be ready for a mid-mechanism break here. Let's evaluate. Oh, you know I like making rings. I think we can finish this before break. It's not a big deal. And this is one where, yeah, it's not exactly a mechanism you've seen before, so we have to think through it. And what's going on? Why don't you focus on this carbon here, which is that carbon there. Yep. It's got a new bond to the aromatic ring, doesn't it? How did that happen? I'd like to point out if that pink position can become a cation, then this will happen. How does that pink position become a cation? Well, you protonate the OH to make it a better leaving group. And we don't use this acid too much until now, but it does work rather well with dehydration reactions to generate cations on carbons. It's not quite a strong acid, but it's strong enough. pKa is close to 2, I believe. And yeah, the water leaves. It's a hint. And I think we're going to do electrophilic aromatic substitution after that on this position here. And generate a cation either here or here. I think we'll put it there because it's more obvious. And let's just get busy. H3PO4. So we'll do the 2 steps to generate the cation. We'll redraw our R group, setting up the electrophilic aromatic substitution. And my computer just loves doing that to me today. If there's a longer pause than normal after this segment, it's because I'm doing a reboot on my computer and it doesn't start up as fast as it used to. I think it needs a reboot. And second step, we're going to make a cation. And we're going to draw out our aromatic ring, which I remember, if I remember correctly, is a meta-trifluoromethylphenyl. So here we go. Here's our R group. And let's have it situated so the trifluoromethyl and the new bond are going to be para to each other because this has to be ortho. It can't reach any other way. So, oh boy, I'm losing my train of thought. I'm going to put the CF3 on top. And the O is here. Goes to a CH2, goes to a C, that's a cation. And we are ready for electrophilic aromatic substitution. Keeping in mind, we also generated a base that we can use for re-aromatization later. I'm just going to go with it. In the old days, they used to just use lines for lone pairs anyway. Some students do still. I have no objections, so I do not object now either. And we're going to generate in a slow step where we lose aromaticity. We have a new ring. Ring size 6. Oh. I'm just going to sigh. And I think that's wrong. Yeah, I'm trying to draw the ring ahead of time, aren't I? CH2, triethyl carbons bonded to the ring carbon. Ring is here to here. And 2 carbons, skip 1, CF3. Figure out where the pi's are. Got a pi here, and we got a pi here. We got a new bond here. We have a cation there. So where's the H that we have to get rid of to make it aromatic again? I believe we're going straight to our final product, which is this species right here. And the H is here. It's always ortho to the cation. More importantly, it's the carbon that made the new bond. This makes a new bond here. This has an H. There's the H. What's going to take that H? The conjugate base of your acid that you started with. Grab H, make pi. It's like an E1 reaction, and this segment is mercifully over. This will take a while. I have to wait for the video to render, then restart, and then I'll get back to you. So don't run away on me. And I will see you then. Oh, gives you more time to think of suggestions for further review because we're moving on to the part D mechanism, and then we're going to be out of things until you give me things. Got it? All right, everybody.